Hello. So we're going to cover section 5.1. So 5.1 is on basic set concepts. So let me give you the definition of a set. We will define a set. Make this. So what is a set? A set. A set is a collection of elements together with a characteristic. So with some characteristic to determine whether a given element, whether a given element belongs to the set. So what this is saying is that we need to have not only a collection of elements, but a characteristic, some unique characteristic about this set that will identify the elements of a set. So just because we have a collection of things or elements or objects or whatever we're looking at, it doesn't make it a set unless there's a specific definition attached to it. So we're gonna look at some examples here. There are different methods for representing sets, so we're gonna talk about two of them. So the different methods. For representing sets, these are the roster method, and then we have the set builder notation. So we have the roster method, the set builder notation. Now the roster method is used if you have a set that does not have many elements, because the roster set method will list every element in the set. So that's good for small sets, but if we have an infinite set, it is more convenient to use, of course, and it wouldn't be possible to list every element, because if we have an infinite set, you have an infinite number of elements, correct? So we will use set builder notation for those sets that have many elements that it's not convenient to list each of them. So let's look at some examples in your workbook. So I'll consider example 1. Let me in fact, you know what, I'm going to, let's do example 1, and I'll also do example 2 because they're different. So let's take a look at example 1. And example 1 is asking for, so let me show you here. It says B is a set of states bordering Texas. So if I use a roster method, I'm gonna list every element of that set. Notice that you have a set with a definition that will identify the elements of the set. So B is a set of every state bordering Texas, and so what are those states? It's going to be Arkansas, Louisiana, New Mexico, and Oklahoma. And I'm going to close the set with these braces. We use braces to represent sets. Now the set builder notation is going to, we can use the set builder notation as follows. We can set B as a set, and I'm going to include the set notation of all the x's. I can use any letter. In fact, I probably should have used S for states, right? But I can use X, and I can say, okay, the set of all the x's, and then a line says such that, this is how you read this line, such that X, and then you're going to write the characteristic here. X is a state bordering Texas. And so that way you do not have to list every state bordering Texas. You just write the characteristic here, and that is set written in set builder notation. So we have the roster method and the set builder notation. Okay, so let me take a look at number 2. So I'll do both because, like I said, they're a little bit different, each one. For number 2, we have R is the set of integers between -2 and 4 inclusively. And so we're gonna do both roster and set builder. Integer is now let's review the integers because you may not remember what they are. So the integers, we can start with 0, and then the positive integers you have 1, 2, 3, 4, and then all the way to infinity, right? And then on the negative side you have -1, -2, -3, and it continues to negative infinity. As you can see, these numbers are not numbers that contain, in other words, these are whole numbers. You can think of them as the whole numbers, but you have to include also the negative numbers and 0, right? And so, which is, you know, part of the whole number. 0 is part of the whole numbers, but not the negatives, correct? So we will end up, but what the integers include both the negative and the 0, and then the positive numbers 1, 2, 3, 4, and then -1, -2, -3, all the way to negative infinity. But now the set that we're looking at is integers between -2. So we're looking at -2 and +4. Inclusive means you're including also the -2 and the 4. So then B, this is the roster method where you list them all. The roster method, you're gonna list them all. So you're gonna start with -2, right? -1, 0, 1, 2, 3, and 4, because it's inclusive. And then if I write it, oh, you know what? This was the set R. I apologize. This was R, not B. And so this is using roster. So this is the roster method. Now the set builder notation. Again, you can say, well, R is a set of all the x's such that, and then you provide the characteristic here. X is an integer, and then you say, and you can say x is an integer between -2 and 4 inclusively. You can just write it, an integer between -2 and 4 inclusive. And then you close the set. So you write the characteristic x is an integer between -2 and 4 inclusive. Close the set with the braces, right? Use braces to represent sets. Okay? So the roster method, you list every integer between -2 and 4 inclusive. And set builder notation, you identify the set by providing the characteristic that defines the elements of the set. Okay? So that's example 2. And so now the next set of examples, we're going to look at them, examples 3A and 3E. So 3A to 3E through 3E. And for each one, 3A, 3B, 3C, 3D, and 3E, we're just going to look at the statement. We're going to read it, and we're going to determine whether or not the collection represents a set. And remember, it has to have a definition. You need to define the elements of the set. You need to have a characteristic that defines the elements of the set. So when we read, I'll just present, I'll put it on the screen here. We read them. 3A is the collection of former mayors of San Antonio. Notice that we can create a set listing the collection of former mayors of San Antonio because you have a list of individuals that have been mayors of San Antonio. So we can create that set. So this is a set, so we're just going to write yes, this is a set. Okay. 3B, I'll put this on the side here, and then we'll just be reading together. The collection of the 5 best restaurants in San Antonio. Well, this is subjective because my set will be different than your set, perhaps, right? Most likely it will be different because I have my own opinions about what are those 5 best restaurants in San Antonio, and your opinion may be different. So this is not a set because there's no unique characteristic definition that identifies the elements of the set. So this is not a set. Okay. 3C, the collection of Ivy Taylor's 5 best restaurants in San Antonio. Yes, because this is a person who can write his or her opinion about the best restaurants in San Antonio. And so we have a yes here. This person can create this list, right? 3D, the collection of young students attending St. Philip's College. We do not know what do they mean by young. They're not telling us what is the age group that they're looking at, so this is not a set. And the collection of students 40 or over attending San Antonio St. Philip's College. So yeah, we can now make a list because we have the starting point, right? So 40 or over, we can create a list. So yes, that is a set. Okay. Okay. Now, let's take a look at example 4A, and I'm gonna do two of those just to explain what they mean there. So let's look at example 4A. And so notice that you see, let me lower the paper and straighten this. The camera likes to make sure that this is straight. Let me make the paper straight. All right, there we go. Okay, so when you see, for example, you see 4A says 3, and then there's the symbol E, right? And then inside there's 1, 3, 7, and 11. Okay. 3 is the E represents element of, so or belongs to. You can think of this E as an element of or belongs to. So you can read this as 3 belongs to this set, and you can see that this is true because the 3 is inside the set as one of the elements, right? So that is true for 4A. Now when you look at 4B, so let's look at 4B. 4B says that 5 belongs to, and then you have the elements 1, 3, 7, and 11. This is false because 5 does not belong to the set. I don't see 5 in there, so this is false. Okay. Okay, so what about 4C? Let's take a look at 4C. It says 15, and then notice that there's a line crossing the E. That means does not belong to, and it says 15 does not belong to, and then you have 1, 3, 5, and then you have 3 dots, which means it continues, the pattern continues all the way to 35. So the question is that because the pattern continues, will 15 be an element of the set? You can see that this is the set of all the odd numbers. So you'll have 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. So 15 will be part of this set. So this statement says that 15 is not an element of the set, but we know that it is an element of the set. Therefore, this is false. Okay. And then you can do 4D and follow the same logic for 4D. All right. Okay. Now I must give you a definition, and this one is on the empty set. So the empty set, first of all, 2 representations. So the empty set, this is the set that has no elements. So the set that has no elements. How do we represent the empty set? The empty set is represented by, so you have two ways of representing the empty set. You can have, it's like a zero kind of with a line through it, or the braces with nothing in them. There's just two ways to represent the empty set. We also call it the null set. So another way to refer to it is the null set. And one way you can, so let me, just write it here. The empty set is also called the null set. So if you see that word null set, then it's referring to the empty set. Okay, now we're gonna look at some examples. Now I'm gonna go through all of these because these are important, and this section may take a little bit of, the videos may get a little longer from now on because the topics are gonna get more difficult. So make sure that you're doing all your homework on time, and remember that if you are struggling, there's tutoring help. There's the link in the in your Canvas course. There's a link that will take you to the Virtual Math World website, where we have a lot of tutors there that are available throughout the week at different times. And also you can schedule a Zoom meeting with me during my office hours, and we can help you if you have questions. Okay, so let's take a look at example 5a. So see, you have the set, and then there's a zero. That's not the empty set, by the way. Meaning that's not the zero doesn't represent the empty set. This is the number 0. And then the question is, which of the following is the empty set? Well, this is not the empty set because the empty set doesn't have any elements. And this set has one element, 0. So this is not the empty set. So not the empty set. Okay, so 5a, no. Now, let's take a look at 5b. Now, some of these may not make sense right away, but after thinking about it carefully, hopefully they do make sense. So we have a set that contains the empty set inside. Okay, but don't be confused by the empty set, because you're not looking at the empty set as a main set. You're looking at this is the main set, the one that has the braces. So this set, the main set, contains one element, and that is the empty set. So the set that we're looking at, the set that we are considering, is not empty because it has one element, and that element is the empty set. You see the difference between the empty set and a set that contains the empty set as its element is not empty. So the set that you're looking at is the one, I'm going to put it in yellow. This is the set you're looking at, and that is the main set, which contains one element, the empty set. So this is not the empty set. Is not empty, right? Okay, now 5C. 5C is pretty obvious because I gave you the notation for the empty set. So this is indeed the empty set because it doesn't have anything. It's just a set without anything. So this is the empty set. You can say this is the empty set, or you can also say the set is empty. Either way, okay? That's 5C. Now let's take a look at 5D. 5D. So you may need to watch these videos more than once. In the beginning, I tend to go a little bit faster. The reason for that is because in the beginning, chapter 1 and chapter 2 also is review. So most of you have had the review material in the past, so I don't go really slowly there because we need to get through that material so we can get to this. Now, this is where really the new topics for most of you will begin, like this chapter on set theory, basic set theory. So we're just going through the surface of the set theory topic, and we're just going through introducing it right now and just kind of go through the main things here. But yeah, so you may require a little bit of more exposure to the material, so you may need to watch the video more than once. Okay, so now what about 5D? 5D is just the number 0. That's just a number. It cannot be a set, so it cannot be the empty set, because it's not even a set, so not the empty set, because that's just the number 0. Okay, now 5E, this one, I had a lot of fun with this one. One time in one of my classes a couple of years ago, I had a student who claimed that this was empty, right? Actually, no, claimed that this was not empty and couldn't see. But let's see. Let's try to understand what this is saying. This is a set that is written in set builder notation, and it says that the set of all those x's such that x is a flying pig. Okay, well, my student was saying, well, this set cannot be empty because x is a flying pig. So the student was assuming existence. So the student was making this assumption, and this is a very dangerous assumption. Do not make this assumption. Just because you read a statement, that implies existence. The fact that you're reading the statement does not imply the existence of the element of that set. For example, just because the set is looking at those elements that are flying pigs does not mean that we are going to be able to find a flying pig anywhere. We know that flying pigs do not exist as we know it today, so this set is empty for that reason, because there's no flying pigs. So this is the empty set. So this is the empty set. Another way to say this is this set is empty. Okay, so this is 5E. And then 5F, it says all the x's such that x is greater than 8 and x is less than or equal to 2. So I have to look at the number line here to know what they are, because I need to know, like, okay, here's 8. Greater than 8 means that from 8 to the right? And less than or equal to 2, so if 2 is here, I'm gonna include the 2 because of the equal sign here, so 2, and then less than or equal to. Okay, now we're saying that the word and, this is very important, make sure you see this, the word and means that x is both. X must be both. X must satisfy both conditions. X has to be greater than 8, and at the same time, that's what and means, x has to be less than or equal to 2. Okay? It's like saying that a person needs to be older than 40 and younger than 20 at the same time. It cannot happen, right? It's either going to be one or the other. If it satisfies one of those two, it cannot satisfy both. So this is empty, because there's no number that will satisfy both conditions. Okay? And 5G, like that technology, right? The cell phone technology, 5G. It gives me the empty set denotation. So this is another way to represent the empty set. So this is the empty set. Okay, so we're done with examples 5. Okay. Moving on to, I'm gonna let you do 6A, 6B, and 6C because we already, well, you know what? Let me do 6B and 6C because you need to know what the natural numbers are. I'll do that, but 6A you can do on your own. Is very similar to what we have done already. So let's do 6C, and I'm gonna do 6B and 6C. So okay, so 6B and 6C. So example 6B says, and I need to write this in roster, so I have to list every element. Okay, so the set B is the set of all the natural numbers greater than 7. Okay, so the set B is a set of all natural numbers greater than 7. The natural numbers, let me give you a list of those, are, they start with 1, 2, 3, 4, 5, and then it keeps going. Some mathematicians began the natural numbers as 0 for proofs, especially when they do the proof by induction. But some of them do that, but most people start with 1. So, okay. But now let's look at the set. I need to list the set of the natural numbers greater than 7, so then I'm going to say B is the set greater than 7, so you have 8, 9, 10, 11, and it keeps going, right? So I can list maybe 4 or 5. Try to list maybe, let's list 5 at least. And then you can put dot, 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 and then close the set with the braces. So this is one way you can write it in roster. Even though it's an infinite set, you can write it using roster method, because if you put a comma after, say, the 5th element, right, and then you write 3 dots to let the reader know that the pattern will continue without bound. That's why I don't put an end here, because there's no way to reach the end. The natural numbers is an infinite set. They grow without bound. Okay, now now 6 and B, that's 6B. Now 6, I'm gonna do 6C. It says that E, let me write it. E is a set of all the x's such that x belongs to the natural numbers. This and means natural numbers, and x is odd. So then that set has to satisfy both conditions. So E, if I write it, so this is in set builder notation, right? This one is in set builder notation. Now, if I want to write it in roster, I'm going to list them. X has to be a natural number and odd. So the first natural number that is odd is 1, and then 3, 5, 7, 9, and then after the 5th element, I can just put a comma after the 5th element, and then write 3 dots to let the reader know that the pattern will continue without bound, will increase, the number continue to increase without bound, and then I close the set with the set notation. Okay, so this is in roster method. This is the roster method, and this one is the set builder method. Okay. Alright, now the next topic I'm going to introduce is the cardinality of a set and finite and infinite sets. So the cardinality of a set, and I'm going to write this down, is the number of distinct elements in a set. For example, if you wanted to look at the cardinality of set E, you would say, well, how many distinct, meaning different, numbers do I see? Well, I can count 1, 2, 3, 4, 5, and then I cannot keep counting because this is going to be an infinite set. So then you can say that the cardinality of this set is infinity because this is an infinite set. If you are able to, on the other hand, if you have a set, for example, say I have the set 0, 0, 1, 1, 1, 2, okay? And I want to look at the cardinality of that set. Well, the cardinality is the number of different elements in a set. What are the different elements of this set? Well, the elements are numbers. And the different elements is 0, 1, and 2. Now, I'm not going to count the repetitions of 0, of 1, and say that I have 1, 2, 3, 4, 5, 6 elements. You don't have 6 elements. You have, for the cardinality, well, you have 6 elements, but not 6 distinct elements. And for cardinality, we're looking at distinct elements. Distinct elements, different. So the cardinality of A is 3 here, because you have 0, 1, and 2, so you have 3 different numbers. So the cardinality of A is 3. How do you represent cardinality using, what kind of notation do we use? We use an N. We use an N for cardinality notation for the symbol. So if I wanted to write the cardinality of set A is 3, I will write an N, and then in parentheses the set A, and I will say that's equal to 3. So I will write N for the number of distinct elements, and then I'll put in parentheses the set that I'm looking at, and then its cardinality. Okay, so let me give you the definition. You need a formal definition for cardinality. I'm going to give you that. And so like I said, this video is going to be a little bit longer than the usual videos, and we should expect that from now on. So I'm trying to make them short, but sometimes that's not possible. Okay, so the cardinality of a set, it is the number of distinct elements in a set. And so an infinite set is a set that has infinite cardinality. Okay, and a finite set is a set that has finite cardinality. What does that mean? That has finite cardinality. That means, this means the cardinality is equal to 0 or some natural number. So this means that the cardinality of the set is 0 or some natural number, like 1, 2, 3, 4, 5, etc. All right, so we have to define those, and then let's see, I have to give you okay, now we're gonna play with this first. Let's practice with these concepts. So remember, cardinality is the number of distinct elements in a set. An infinite set has an infinite cardinality, and a finite set has a finite cardinality, 0 or some other natural number. So we will try some of the examples here. Let's look at 5. Let me do cardinality of, okay, let's look at 7a. 7a, we have the set is equal to 1, 1, 2, 3, 5, and 8. Remember, so for cardinality, I'm going to write n of a. The cardinality is going to be 1, 2, 3, 4, 5, right? So you have 5 different numbers, so it's 5 for 7a. For 7b, we have B is the empty set. So B is a set, and it's equal to the empty set. So what is the cardinality of B? Remember, the empty set has no elements. So if I look at its cardinality, it has to be 0 because there's no elements, right? So this is 0. For the cardinality of B is 0. Why? Because B is the empty set. Okay, oops, sorry, the empty set. Okay, okay, now what about 7c? Okay, let's see, 7c, you have a set is equal to the set of all the x's. X is a natural number and x is less than 7. Well, you have the set less than 7, so you're gonna have an infinite set here, right? So, actually, this is greater than 7. Wait, which one I'm doing? 7C. No, C. Yeah, I'm good. Less than 7. So, okay. Actually, this is gonna be a finite set, right? So, what is the set? Let's list the elements. Let me raise this a little bit. So let's list the elements. X is a natural number and less than 7. So it's gonna be 1, 2, 3, 4, 5, 6. Less than 7. So I cannot include 7. So then the cardinality of C is gonna be 1, 2, 3, 4, 5, 6. How many numbers? 1, 2, 3, 4, 5, 6, and they're all different, so this is going to be 6. Right? So that's that. And then if you look at 7D, let's look at 7D. Look at 7D here. When you look at 7D, D is equal to the empty set, right? And so you see that there's one, you're looking at this set, this is the main set, there's one element there, so the cardinality of D is going to be 1. Okay. Now 8A is pretty obvious, you know, you have set A, X is a US state, so the cardinality is equal to 50 there, right? And then 8B, try 8B, because I have done examples like that, and I'll let you try 8B, 8C. Well, actually, let me do, I'll do 8C, and then you can do D based on that. So 8C, it says C is a set, all the x's such that x is a natural number, and also x is greater than 7. Well, you have, if you list them, you can see that this is going to be a natural number greater than 7, so that's 8, 9, 10, 11, 12, and then it's going to continue. So I write the 3 dots for the pattern and put the set notation. This is an infinite set, so you're going to say the cardinality of C is infinite. So you just write infinity for the cardinality. Okay. So that's, and the last concept, so that I don't make this video too long, let me give you the last definition. We have two definitions. Equivalent sets and equal sets. Equivalent sets are sets that have the same cardinality, and equal sets must have the same cardinality and exactly the same elements. So equivalent sets are sets that have the same cardinality and equal sets are sets that have the same cardinality and the same elements. So identical elements. Sets that have the same cardinality and identical elements. So these are the last two definitions, and we're gonna look at some examples. We want to determine if they're equivalent. And okay, so I'll do 9A, and then you guys can do 9B. So let me do 9A. It says determine if the sets are equivalent. We have W as a set of all the x's such that x is a day of the week. And then F is a set of all the x's such that x is a month with exactly 31 days. Now, if you look at the months that have 31 days, you have 7 of them. and W, X is a day of the week. We have 7 days, right? So the cardinality of W is 7, and the cardinality of F is also 7, right? So you have both cardinalities the same, and what does that mean? This means that they are equivalent sets. Once again, the cardinality refers to the number of distinct elements. The number of distinct elements. W is looking at the days of the week, so you have 7 different days. F is looking at months with 31 days. If you look at the calendar, you're going to find the Gregorian calendar, you're going to find that you have 7 months that have 31 days. Therefore, both of the sets have the same cardinality, and that makes them equivalent sets. They're not equal because they do not have identical elements. They are only equivalent because they have the same cardinality. Cardinality is the number of distinct elements in a set. Okay? All right. Now, I'm going to look at one last example, because I don't want to make this video too long. It's already 41 minutes. So let's look at the first example 11, and then you can do the others. We're looking at, this is the last example of this section 5.1, and I'm looking at A equals the set that has 4, 4, 4, 4, and then 3, 3, and then 2, and then 1, 1, 1, and then 0, 0. That's set B, A. And set B is a set 0, 1, 2, 3, and 4. Okay. Now, you're looking at, let's look at the cardinality of A, and we are only going to count the different numbers. So 4, 3, 2, 1, and 0. So you have 1, 2, 3, 4. Cardinality is 4, right? And then for B, the cardinality is 1, 2, 3, 4, 5. Oh, you know what? For A also, because you have 1, 2, 3. I missed the 2. 4, 5. So the cardinality of A is 5. The cardinality of A is 5. Why? There's 5 different numbers. The 4, the 3, the 2, the 1, and the 0. The cardinality of B is also 5 because there's 5 different numbers. Because they have the same cardinality, these are equivalent sets. Okay. The question is, are they equal also? Do they have identical numbers? Yes, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. They are also equal sets because they have identical numbers. Even if they're not written in the same order, they're identical numbers. So remember then that equal sets must have the same cardinality. Equal sets, you're looking at two things. Okay, for equivalent sets, you're only looking at the cardinalities to be the same, right? So this one, they're equivalent. But why are they also equal? Because they have both conditions, the same cardinality, and the same elements. Okay? So don't forget the distinction between equivalent, which is only with the same cardinality, and equal sets must have both same cardinality and identical elements. Okay? All right, guys. So we are at 43 minutes and 55 seconds. I'm going to stop here. Remember that this week, well, by the time you watch this video, you probably would have taken the first exam. Yeah, let's stop here. I'm going to make another video for sections 5.2 and 5.3. I may combine the sections. It depends on how long 5.2, how long it takes me. But as you can see, I went through this material a lot slower than the way I normally do, because the other material was a lot easier, right? It was review material. Okay, God bless you all, and I will see you, well, cannot see you, but you'll hear from me soon. Take care and have a blessed day. Bye-bye.